Hello everyone, how are you? Welcome to your favorite channel, Maths Zone African Motives. Today we want to dive deep into physical sciences. This is for grade 10. So today I want to introduce a series of videos for a topic that is actually done in term 3 as well as in term 4. So instead of just starting with mechanical energy, a topic that you refer to as mechanical energy, I chose to start this series from its founding basics. So you're going to see that there is a topic in physical science that we refer to as mechanics. And you will see that mechanics actually comprises of vectors and scalar quantities, motion in one dimension, as well as your energy, which is your mechanical energy, which is the sum of gravitational potential energy and kinetic energy. So this topic actually houses subtopics within it. Like for example, on your grade 10 syllabus, you would know that you have got what we refer to as vectors and scalar quantities. And then after vectors and scalar quantities, you have what we refer to as motion in one dimension. And then you have what we refer to as mechanical energy. So I want us to start by defining what mechanics is so that we can actually get to have a clear understanding from the basics of mechanics so that you understand from where it started up until where it will actually get to lead us where we refer to as what mechanical energy. So this video will actually get to focus on the basics. We are going to start by defining mechanics, and then we'll go into defining physical quantities, group them into two broad groups, which are your vectors and your scalar quantities. From there, we will list down the examples which fall under each, and then we get to go deep into vectors or else vector quantities, how we represent them and how we calculate them, or else how we solve for what we refer to as the resultant vector. And then thereafter, we are going to do a conclusion with a practice exercise to check comprehension of what would have done. So the main major part of this video is to introduce the major basics of what we refer to as mechanics. After this video, we are going to dive deep into motion in one dimension. After motion in one dimension, that's when we are now going to do a topic which is referred to as mechanical energy. This is a topic that you are supposed to be doing in your term 4. So it's easier to understand mechanical energy once you now know and you now have the basics where it starts. Just like your chemistry part, you start from atoms, bonding, and then you later go to quantitative aspects of chemistry, and then you later go to types of reactions. So without knowing bonding, without knowing atoms, without the basic understanding of what we refer to as elements, you cannot be able to understand acids and bases. You cannot be able to understand the quantitative aspects of chemistry. That's the same thing when it comes to paper one, which is your physics part. As long as you do not know the nitty gritties to do with mechanics, the basics part, at the end of the day, you find it difficult to understand what we refer to as mechanical energy, how we calculate it, because you would need to know motion in one dimension. You also need to know how to classify quantities as scalar as well as vector quantities. So without wasting time, let's get started. So I would start to say that, so today this video, I brought some notes. So I'll be explaining some notes. That is what we refer to as basics, so that you get to have a clear understanding of where we are coming from and where we are going. So let's start by defining the word mechanics itself. So you will see that mechanics is just the branch of physics that focuses on the motion of objects as well as the forces that act on them. So what we refer to as mechanics, this is motion of objects. So from the word itself, mechanics, This is where it was derived from motion. So motion of objects as well as the forces that act on it, that is what we refer to as mechanics. So mechanics is best described using different physical quantities. And what do we refer to as physical quantities? These are measurable quantities of objects. So you get to see that we come in contact with many physical quantities in our natural world daily. For example, things like your time, the progress that you make each and every day, mass, the amount or else the total amount of matter in an object, weight, which is your mass being attracted to the center of the earth, force, which is either a push or a pull, and then we've got electric charges, or else electric charge, for example. I'm sure you've done this experiment where you get to rub your latex ruler on your head, and then you start picking up paper using that ruler. It's because when you rub that ruler on your head, you are actually charging it. So what we refer to as that electric charge, that is what is causing that attraction. So physical quantities are just measurable quantities of an object. We want to measure how much the total amount of matter in an object. That is what we refer to as what? As mass. And then how much progress are we making? That is what we refer to as time. And then what is the force that is pulling you towards the center of the earth, which is actually defined by what? By mg. That becomes your weight. So you will see that these physical quantities, we get to break them down into two broad groups, which we refer to them as what? Vectors and what? And scalars. So we usually get to call these vector quantities and scalar quantities. And what are vector quantities and what are scalar quantities? So you get to say that vector quantities are quantities that have got both magnitude and direction, or else quantities that can be fully described, quantities that can be fully described by mentioning both magnitude and what? And direction. That is what we refer to as what? As vector quantities. For example, you have got your force. You know that force can either be a push, meaning to say that it's either you are pushing towards the right or else the left, or else we can say to the east or else to the west. That's direction. So when you are mentioning force, you actually get to say 5 newtons east. So you mention both its magnitude and its what? Its direction. And then when it comes to weight, you know that weight is the gravitational force that attracts your body towards the center of the earth. So that part where we said towards the center of the earth, we are saying that that defines our direction. So if you want to know the weight of a person, which becomes 10 newtons, it's 10 newton force towards the center of the what? Of the earth. So the 10 newton becomes your magnitude, and then towards the center of the earth becomes the direction in which it is what? It is directed. So even if we also get to know of displacement, when you are defining displacement, we define displacement as the shortest straight line distance in between 2 points. So when you say shortest straight line distance between 2 points, you are actually looking at the distance towards a certain direction, as well as your velocity has got both magnitude and what? And direction. Acceleration, magnitude and direction. But now, what about quantities which only have got magnitude, which is size? So you will see that magnitude is what we refer to as size. Like for example, mass, you cannot say 10 kg to the east or else 10 kgs to the north. You cannot say that. So when you want to actually get to describe the mass of an object, you just get to say that there is 10 kgs of rice. So what does 10 kgs of rice mean? It simply means the total amount of matter within that 10 kg sack of rice. How much those small pieces of rice are they? They total to what? To 10 kgs. So you only mention its magnitude only. So that is what we refer to as scalar quantities. Quantities in which you only mention their what? Their magnitude. These, they have no direction. So the difference between scalar quantities and vector quantities is that scalar quantities, they have no direction. But as for vector quantities, you need to mention both its magnitude as well as its direction. So the other examples of scalar quantities comes to say time. You cannot say that it's 10 hours to the north, but you only mention the progress that is occurred. Like for example, from the time that I started reading up until now, I've actually read for 5 hours. You only mention the total time that you have been reading. Maybe we left Johannesburg at around 10 p.m. and then we arrived in Bloemfontein at around 1 a.m. So you are only mentioning the magnitude. So that will relate to say how many hours did you take to travel from Johannesburg to what? To Bloemfontein. You only mention the total time that you traveled. There is no need of saying towards the west, the east, or else going to. It's just how many hours did you take. So there is also charge and also energy, distance, and speed. Because we are saying that distance is just the total length of the whole path that you took. Unlike displacement, where we say it's a straight line path, where we are saying that you need to define the straight line distance between A and B. So you mention displacement relative to a reference point. Like for example, if you started at A, you would say that B is 10 meters east of what? Of A. So there is direction there. But when it comes to distance, let's say that you did not move in this straight line. Maybe you started by going down, you later came back, and then you went up, and then you later came back to B. We assume that maybe there is no straight line road. We would need to know the total length of you moving from here, going down, going up, and later reaching B. So that is what we refer to as what? As distance. So you can see that distance does not have direction. At some point in time, you went down and then you later went up, but you ended up in the east direction. So there is no direction there. It's as if you are moving in a haphazard manner. So when it comes to distance, we don't actually necessarily need to know the direction. We only need to know the total path that was moved, the total distance that was covered. So that is what we refer to as vector quantities as well as scalar quantities. So these are the examples of vector quantities, and these are the examples of what? Of scalar quantities. And then you get to see that since we have mentioned that when it comes to vector quantities, we need to mention both the magnitude as well as the what? As well as the direction. Now, vectors, they now become special physical quantities, where if you now want to represent them, we can actually get to represent them using arrows, where the arrow actually has got the magnitude being represented by the total length of that arrow, and then the direction being represented by the what? By the arrowhead. Like for example, here we actually get to say that we have got the tail of that vector, meaning to say that you need to first define the reference point, where we are saying that this is where we started. So this becomes our tail. Like you know, the tail of all those animals that you know, the tail is always at the back. So we get to say this is where we started. And then this is where we ended. So this becomes our head. But you can see that on our head, we actually have got an arrow pointing towards a certain direction. So this arrow is pointing to the what? To the east. So the arrowhead actually what? Shows direction. But the total length from your head to your tail, or else from your tail to your head, represents the magnitude of that vector quantity. So at some point in time, you will be asked to represent graphically your what? Your vector. So when you are representing graphically your vector, you need to first determine the point of reference, or else the reference point, which we usually refer to as the what? As the frame of reference. And then you get to choose direction. Which one becomes positive? Which one becomes negative? And then you just get to use an arrow that has got an arrowhead pointing towards the direction of that vector. So you will see that by mentioning that, we actually get to define that what we refer to as equal vectors. Let's say you have got equal vectors, 10 Newton to the east, 10 Newton to the east. It's those are equal vectors. We have got 10 newtons force, a force of 10 Newton, which was applied maybe to an object to the east, and then also a force of 10 newtons, which was also applied as pulling towards the east. These are equal vectors. How do we represent equal vectors? Using this notation, you will see that equal vectors, they have the same length and also the same what? The same direction. As long as you are going to actually get to have the same length within this arrow, and then the arrow pointing the same direction, that is what we refer to as equal vectors. And then within our vectors, we will have what we refer to as positive and negative vectors. The positive and negative comes in reference to the direction that you would have chosen to be positive. So if you say your east is positive, it simply means that any vector that is pointing opposite to this direction becomes negative. And then due to that, now we now get to define our direction in different terms. We have got different terms of referring our direction, or else that gets to give reference to our direction. We can either use what we refer to as a relative direction. Relative direction has to do with up or else down. We know that this is up and this is going what? This is going down. That is relative direction. Or else we know that if you are going this side, you are going to the right. And then if you are going that side, you are going to the left. This is what we are used to. This is just normal notation. That is what we refer to as relative direction, because we usually use our right hand, our left hand to point directions. We usually use our hands to say up, to say down. So that is what we refer to as what? Relative direction. So you can choose to represent your direction in terms of relative directions, or else you can choose to represent your direction in terms of the what? Of the compass. When you represent your direction in terms of the compass, you now know that when you actually take your compass will be more like this. This arrow that points up, we refer to it as north. That is the northward direction. The arrow that points towards the right, we call it what? East. This is the eastward direction. And then that points down becomes your what? Your south. And then the one that points left becomes your west. So that is how you can choose to represent your direction, or else to refer your direction as. You can either use the notation of what? Of the compass, which is north, east, south, west, or else relative direction, which is up, right, down, left. But when you choose your reference of direction, make sure that you are consistent. Don't say that at some point in time you say up, and then at some point in time you say east. When you want to use relative direction, be consistent. Actually go on with relative direction. Now use up, down, or right, or left. But if you choose the compass, keep consistency in the compass. Every notation of yours has to be referred to the compass. To say up will be north, down will be south, and then right will be east, left will be what? Will be west. Don't interchange those. Be consistent with the type of reference in terms of direction that you have chosen. And then lastly, we have what we refer to as bearing directions. These ones, they are actually named in reference to what we refer to as a fixed point. What do I mean by that? We usually get to choose our north, and then we usually get to say that if I want to actually take note of the direction maybe of an object that is here on B, I would actually get to measure the angle that I have from my north going clockwise up until I reach point B. And if I find this angle, let's say maybe it's just what, 120 degrees, my direction would be 120 degrees in terms of my what, of my bearing. What it simply means that is that my object is 120 away from the north. So that is what we refer to as what, bearing direction. So these are the types of what, of reference, or else let's get to say frame of reference when you are referring to your direction. So these are your reference point when it comes to direction. That is how we define our direction. We can either define our direction in terms of relative direction, or else we can use the compass, or else we can use the bearing. But the normal notation becomes relative direction or else compass direction. That is what we usually use. And if you choose either of that, please make sure that you are consistent with your choice. Now, like I mentioned, I said that at some point in time, they will ask you to draw vector quantities. So when you are drawing a vector quantity, let's say that you want to represent a vector graphically. What you need to do, there are certain steps that you need to follow. First, you need to decide upon a scale and you need to write it down. Let's say that I have got, I'll keep on using the simplest vector, which is force. I've got a force that is being applied, and this force has got a magnitude of 10 newtons. And you can see that this force is towards the what? The east. So what you need to do here, when you want to represent this vector, you need to choose scale. What do I mean by scale? We said that a vector can just be represented by an arrow, and that arrow would be having magnitude as well as direction being represented by the arrowhead. So this magnitude is what we want to define by defining our scale. So scale actually refers to the scale would give you reference to your what? To your magnitude. So when you choose scale, for example, you can come and say that let maybe 1 centimeter length represent 1 Newton. So it simply means that my 10 newtons would be equal to what? To 10 centimeters. So if I'm representing this vector, I will need to choose, I will need to actually get to what? To draw, let me get to say that I will need to draw an arrow that is of what? 10 meters, 10 centimeters in length. So I wanted to actually get to pick a line here. Let me just get to use this so that I can use it for as an example. So let's say I want to represent this vector, and this vector I can see that it's a what? It's a 10 Newton force that is directed towards the east, and I've chosen a scale that is saying let 1 centimeter be equal to 1 Newton. How will I come to represent this? This is where I would actually get to say that where I would draw my 10 centimeters like this. This is my 10 centimeters. This simply means that I've drawn a vector of 10 newtons. So I chose a scale to say 1 centimeter will represent 1 Newton. So if I draw an arrow that is having a total length of 10 centimeters, it means that the magnitude of my vector here is equal to 10 newtons, because I know that 1 centimeter represent what? 1 Newton. So the magnitude of this vector is equal to 10 Newton. So the first thing that you need to do is to actually get to what? To choose your scale. After choosing your scale, you write it down. So let me say, first step, choose scale. So we said let what? Let 1 centimeter be equal to what? To 1 Newton. So 1 centimeter will represent what? 1 Newton. Now, you now need to decide on a referenced direction. What do we mean by reference direction? We want to go, or else we are going to the east. As we are going to the east, we can actually get to say the east, let it be the positive direction. So if I've got a force of 10 newtons towards the east, I would know that my line would actually, or else let me say, my arrow would be pointed towards the east, so that I would actually get to measure my length starting from this tail to my head. Once I know this total length, then I can know the magnitude. But I already know the what? The direction. So you decide on the reference direction. After that, you need to determine the length of the arrow representing the vector by using the scale. So if you are given an arrow like this, you can come and use your ruler. You measure this length. You measure this length. If this length is equal to 10 centimeters, it simply means that by your scale, 10 centimeters will be representing what? 10 newtons. And then the other thing now is to say you draw the vector as an arrow line. So these steps, they are just actually stating what I've just done here. So the vector will be drawn as an arrow line like this. So this becomes your vector at the end of the day. So the first thing is you need to choose your scale. After choosing your scale, you write it down, and then you later choose a reference what? Direction. And then you would know that the length of a line that you want to draw has to represent the magnitude of that vector. So you now get to convert this vector into a total length. And then you just get to draw the vector as a narrow line. And make sure that you fill in the arrowhead, which is this one. And then that becomes your what? That becomes your vector. So for example, let me use this example that is given here. They said draw the following vector quantity, which is saying displacement is equals to 16 kilometer east. So 16 kilometer east, I said that what I'll start doing, let me just get to delete this. Sorry. I want to delete that. Now I'm trying to see how I can actually get to delete that. So, all right, just pardon me there. So we want to delete that one. We've managed to. Now, before we can do anything, our vector is displacement, and it's what? 16 kilometers to the east. Now, the first step is to determine what? Your scale. So let maybe 1 centimeter represent what? 4 kilometers. Why? Because I know that 16 is actually what? Is actually a multiple of 4. So I would know that at least if I say 1 centimeter represent 4 kilometers, I can be able to know the total length, and that total length can be a whole number. So how many centimeters would be equal to 16 kilometers? You will now come and divide 16 kilometers by what? By 4 kilometers. So that you can actually get to say 4 into 16, you would know that this would be equivalent to what? To 4 centimeters. So you've got your scale. Having your scale, you have now determined the length of that vector. Now you now need to decide on the reference direction. So your reference direction, it's going to the east. So it's going to be towards the east. Now, you now get to draw that vector as a narrow line. And make sure that you fill the what? The arrowhead. So I'm going to take my line here, and that line is supposed to start here. Let me say that this becomes my reference point, and then I am supposed to go to the east, and towards the east, this line is just to be what? 4 centimeters in length. By doing that, I've represented my what? My vector, which is what? Displacement, being equal to 16 kilometers towards the east. And I've chosen a scale to say my scale is what? My scale is going to be 1 centimeter represents 4 kilometers. So my 16 kilometers will be represented by 4 centimeters. If that is the case, I need to come here and draw a line that is what? That is 4 centimeters in length. And it has got an arrowhead pointing towards the east. So that is simply how you draw or represent vectors. Now, when it comes to vectors, once we have got 2 or more vectors acting upon an object, just get to know that at the end of the day, we will have what we refer to as the resultant vector. So there is something that we refer to as a resultant vector, where we are saying that vectors can either be added or subtracted. And also we would know that their magnitudes can also be multiplied. But when you add or subtract vectors, you will get something that we refer to as the what? As the resultant vector. When you get a resultant vector, what is it that we mean by a resultant vector? We are saying that a resultant vector is that single vector that has the same effect as many separate or individual vectors. For example, let's take object A here. You can see that I've got this vector F1 that is pointed towards the east, and vector F2 pointed towards the east, acting upon the same object. And these two vectors, I need to know their resultant. What effect are they going to actually cause on this object? That is what we refer to as the resultant. So the resultant can now be calculated or be given by what? By our F total, where I would come and add F1 and F2. But when it comes to addition and subtraction, we need to first determine our what? Our reference direction, as we have said. Already we are given the arrowheads. So now we need to get to say, let positive direction be towards the east. So if positive direction is towards the east, a vector that is pointed towards the east will be carrying a positive sign. So if it's carrying a positive sign, I would know that F1 is a positive, F2 is a positive. So for me to find the total vector there, it will be F1 plus F2, and these are both positives. But at some point in time, let's go to object B. You can see object B, the other vector is pointed towards the west, whilst the other one is pointed towards the east. So the one that is pointed towards the east carries a positive value. So that when you come here, you add F1 and F2, you would actually have this one having a negative. That's why here they actually said F2 plus F1, but F1 is carrying a what? A negative direction. So that negative direction actually comes to become a negative here when you are summing up. So that the magnitude becomes a negative here. So that at the end of the day, you would have F2 minus F1. So if you subtract the two vectors, you would also get your what? Your resultant. Because these two vectors, they are in two different what? Two different directions. So that is what we mean by vectors can be added or subtracted. So when vectors are added or subtracted, you get something that we refer to as the resultant vector. And the resultant vector is that single vector that has the same effect with multiple what? With multiple separate vectors, or else two or more separate vectors. So you would see that resultant vectors can be determined either graphically using tail to head, or else tail to tail methods, or else by calculation. Now let's see how you would actually calculate your resultant vector. So let's say that I would skip this slide for a bit. You want to calculate your resultant. You can either use graphical method. So the graphical method that I would take here, it's tail to head method, where I would get to say that the first step that you need to do is to draw the first vector with an arrow that indicates its direction. Then the length of the arrow should represent the magnitude of the vector. Meaning to say that if I've got a vector that is acting towards the east, which is equal to 60 Newton in magnitude, I would come and actually get to determine my scale, which is to say let 1 centimeter be equal to 10 Newtons. So maybe at some point in time, I would say let 1 centimeter, let me use this space, let 1 centimeter, that is my what? That is my scale. Always we start by choosing scale and then we write it down. So we are saying let 1 centimeter represent 10 newtons. And then you now need to choose your reference point where you are starting. So I can choose to actually get to start here, as you can see. And then I would need to draw my what? My vector here, which is 60 Newton, using this what? This arrowhead method to say that I will represent my arrow with a magnitude of what? If I've got 1 centimeter representing 10 newtons, I would have 60 newtons being equivalent to what? To 6 centimeters. So here my magnitude would be 6 centimeters. So this arrow has to have a length of 6 centimeters. So from here, I would be having a length of what? Of 6 centimeters. And then for another vector of 90 newtons, I would also come now and start. So now they're saying next, draw the second vector starting from the head or arrow tip of the first vector. So this is the head or the arrow tip of the second vector. So we know that this is our tail and this is our head. So on your head of the first vector, that is where you start, because initially you chose your reference point to be this one. After choosing your reference point, that's when now you drew your first vector. Your second vector now, its reference point becomes the head of the first vector. That is where you start. And then since you said, let's get to say that your vector that is going towards the east would be drawn going this side. The vector that is towards the west will be drawing going that side. So if 90 Newton is towards the east, you will start drawing it from this arrowhead, and then you draw 9 centimeters towards the east. So the length of this line or of this arrow has to be 9 centimeters. So to find the resultant vector now, you now need to draw an arrow from the tail, starting from the point of the first vector, that is the tail of the first vector, going to the what? To the head of the second vector, which becomes this one. Now, if I now want to draw my arrow, I'll start here. And then I'm now drawing my arrow here, starting there. And then I would go to the what? To the head of the second vector. And that becomes what? That becomes my total length. So you can see that here I did not draw my vectors up to scale. But this is how you would have found your resultant. This now becomes your resultant. So let me just get to delete this because it does not represent my what? My actual drawings there. So what I'm going to do instead, I'm going to start all over for this example so that you can see what we are saying. So we said that initially you choose your scale. That is the rule of drawing a vector. So if you say your scale is 1 centimeter is equals to 10 Newton, and then you have got a 60 Newton force going towards the east, a 90 Newton force going towards the east. You start by drawing the first vector, which is F1, would simply be represented by what? By 6 centimeters. The second vector will simply be represented by what? By 9 centimeters. Now, when you are drawing these ones, you would come here. You start, this becomes your reference point, and then you draw 6 centimeters going towards the what? The east. That is your 6 centimeters. That becomes F1. So I've represented my F1 there, which is what? 60 Newton. And I know that 60 Newton is what? 6 centimeters. The second vector, when I want to draw my second vector, I'll start from this arrowhead. And then from that arrowhead, just pardon me there, I want to do something neat. So I'll start on my arrowhead. So this becomes my arrowhead. And then on that arrowhead, I need to draw my line also, which has to be what? 9 centimeters. I assume here I've done. Okay, fine. Let me try to do something here. Yes. Yes, I think now I've correctly done it. Now I will say this becomes my vector 2, which is what? 90 Newton. Now, for me to find the resultant vector using this graphical method, all I now need to do is to draw my resultant vector starting from the what? I would actually get to say this is my starting point, where I will say that this is the tail of my what? This is the tail of my first vector. Pardon me there. I need to actually get to first determine this. Let me draw a line that will help me to actually get to, yes, something like that, so that I know where I'm starting. And then I would know where I need to be ending, right? Let's do this together, guys. So I'm starting here, and then when I start from the tail of my first vector, I will need to actually get to end on the what? On the head of my what? Of my second vector. So this was just supposed to be what? To be 15 centimeters, if I'm not mistaken. So let me try to align it. You only need to, right. I'm sure now I've aligned my vectors. Yes. I've tried to align my vectors. So that is simply how you get to draw your resultant vector, or to determine your resultant vector. You draw your first vector, and then your second starting from the arrowhead, and then your resultant has to start from the tail of the first and go to the head of the what? Of the second. And then this total distance here that you have here, this total length that you have from here to there, now becomes your what? Your resultant. That becomes your resultant. So if they say determine your resultant using the graphical method, that is how you simply do it. So let's go to the next method. The next method will now be algebraic method, or else by calculation. At some point in time, they will say use calculations to actually get to calculate your resultant. So when you are doing calculations, you need to first determine your reference direction. When we say reference direction, we are saying choose a direction that you want it to be positive. Like, for example, choose the east to be positive. I usually like going to the right to be chosen as positive, so that people, they get used to saying positive is the right, and then negative is the left, or else positive is the east and negative is the west. And then after that, to find the resultant, you now need to sum the two vectors. So for example, I've got vector 1. My vector 1, it's F1, it's 20 Newton. But this 20 Newton, it's what? It's towards the west. Since it's towards the west, this becomes a negative 20 Newton. And then I've got vector 2, and my vector 2, so mind you, this arrow that you find on top of every vector simply represent this physical quantity to be a vector. That is how we represent a vector, by using an arrow on top of what? Like for example, I would have my displacement like that, my velocity like that, my force like that. This arrow simply actually determines that this physical quantity has got both magnitude and its what? And its direction. So now my vector 2, which is this one, it's going to the east. So this is 50 Newton to the east. So this one becomes a positive 15 Newtons. And then my resultant vector now becomes F1 plus F2. But I know that F1 is a negative 20. And then F2 is a positive 15. So at some point in time, it's negative 20 plus 15. That becomes what? Negative 5 Newtons. And since I said negative means west, so this is just 5 Newtons what? West. But the example that I have here, you can see that themselves, they chose a reference direction by using your compass. I used the compass, they used the relative direction. They said to the left or else to the right. So they chose to the right to be what? They chose to the right to be positive. So that when they said this one is going to the right, it's a positive, and then this one is going to the left, it's a negative. So they later came and said F1, if you actually get to say F resultant is equal to F1 plus F2, you would see that F1 it's a negative, so it becomes negative F1 plus F2. F2 is a positive. So they just came and said 20, negative 20 Newtons plus positive 15. And then they found negative 5 Newtons. But because they already chose the left hand side to be a negative, so it simply means that my resultant is 5 Newtons what? Left. Because that is how I defined my direction. So you need to choose your reference direction. Do you want to choose relative direction, to use right or left as your direction? Right or left. And when you use right or left, say right is positive and left is negative. But if you choose the compass where you have got north, east, and then you have got west, just get to choose maybe east to be positive and west to be negative. After doing that, look at your vectors. Where are they pointing? Where they are pointing, determine their direction by where they are pointing. So that is how we actually get to determine our resultant vectors, by either using graphical method or else what? Numerical method, which is just by calculation, or else by algebraic calculations. Now, let's actually get to see our practice exercise. But before that, remember there is something that I skipped, and then I say that I would come back to it. This is to do with resultant and equilibriant vectors. So after finding your resultant, there is something that we refer to or call an equilibriant. What is an equilibriant? An equilibriant, this is the equilibrium that is reached between your system, where we are saying that if it's an object and there are two forces acting on it, there is no movement which is supposed to occur there. So for us to have no movement, we need to actually get to what? To add a balancing force. So that balancing vector becomes our equilibriant. So our equilibriant can be defined as the vector that has the same magnitude but opposite direction to the resultant vector. It's balancing, so it has to have the same magnitude, but it has to be in the opposite direction. For example, if I have got 5 newtons, my resultant, let's say my resultant, it's 5 newtons towards the what? That other time we determined our resultant to be 5 newtons towards the west. Let me use that. Let's say my resultant, it's 5 newtons towards the west. That is my resultant. Then it simply means that my equilibriant has to be 5 newtons towards the east. Why? Because I want to balance this force or else this vector. So my equilibriant becomes equal in magnitude to the resultant, but opposite in direction. So we define our equilibriant as that vector that has the same magnitude as the resultant, but it's opposite in direction. Now, let's go to our practice exercise so that we can be able to check comprehension. How far did we understand whatsoever that we were doing? So this is our practice question. So allow me to actually get to what? To move this towards this side, so that we can use the space this side. So the first one is saying, a car breaks down on the road. So let's say that you have got a car. I'll simply draw a car that we used to draw when we were in preschool. So forgive me there if I don't represent it as much as you would wish me to have done. But I'm sure using our preschool diagrams, we can understand each other. So this is my car. So a car breaks down on the road, and you and your friend who happen to be walking past help the driver to push start it. You and your friend stand together at the rear of the car. So you stand together, let's get to say what? Behind here. And then you actually get to what? You push with a force of 50 Newton. So you and your friend, you are here. You are pushing this car because you want to help this driver to actually get to what? To push start his car, because the car is broken down. So maybe if you help the guy to push, at some point in time, it can actually get to what? To push start. So here they're saying you push with the force of 50 newtons, and then your friend pushes with the force of what? 45 newtons. What is the resultant force on the car? Use the head to tail technique to calculate the answer graphically. So the first thing that you need to do is to determine your scale. So on our scale, let 1 centimeter represent what? 10 newtons. So that this first vector, which is your let's say first vector, your force would be 50 newtons, would be represented by what? If I say 50 divided by 10, I would get 5 centimeters in magnitude. Your second vector, which is F2, the one of your friend, it's 45 newtons. Let me say 45 divided by 10, that would be what? 4.5 centimeters. So these are your two vectors. After having your two vectors, you now need to determine your point of reference, your reference point. Let's say this is my reference point. This is my starting point. And then we need to go towards the east, like I've drawn this car. This car is going to directed to the east. So I'm going to draw all of my vectors going to the east, because you and your friend, you are pushing in the same direction. So the first vector has to be what? So I will draw a sketch to represent. So I will represent my first vector towards the east, and my second vector. So my first vector here, which is F1, which is towards the east, is supposed to be equal to 50 Newton. And then the second vector, which will start from here, which is the head of my first vector towards the east as well, is supposed to be what? F2 is supposed to be equal to 45 newtons. Now, for me to draw this, I will need to actually get to take my ruler and actually my pencil. I'll start here. This is my reference point. So maybe let me start by drawing, maybe let's get to say a straight line point. I would choose to say I assume that this is a straight line. And then I choose to start. Maybe I was not supposed to end here because this one. So since my vector, let me just get to draw what I had drawn there. My vectors are going in that direction. So the first one, it's actually 5 centimeters in length. So I'll need to draw 5 centimeters in length starting from my starting point. So I will draw my 5 centimeters going to the east. And then now I would also choose to say I will need to, because this one has to be 5. Now I will need to draw another one. So when I'm now drawing the second vector, we said you start from the head of the first going to where you are going. So the second vector will start here. And then starting from there, I have to draw how many centimeters? I'm actually drawing 4.5 centimeters. Just pardon me, guys. My instruments at some point in time, they tend to misbehave. So I'll be trying by all means to just get to depict or else to represent these things as simpler as they can be so that at least you can be able to follow. So I'll be just trying to make them representable here. So just pardon me, have patience with me. So we need to draw another line which is 4.5 centimeters in length going to the east, starting from the head of our first. So if we're starting from the head of our first, yes, we'll be starting there, and then we need 4.5. So that becomes what? 4.5. Now, to determine, so at some point in time, I've drawn my first vector. This is my first vector, which is 50 Newton. My second vector, which is what? So my first vector was 50, my second is 45 Newton. So now I now need to draw my resultant. So my resultant has to start where I started here. And then it has to go where I ended on my second what? Vector. So I started there. Yo. Um, let's try patience. So I started there. It shows that I started, you see now. The problem would be to say I actually want to start exactly where I started so that it can represent my vector clearly. So I started, let's get to say I started there, and then I was supposed to have ended where? I ended there. So that becomes my what? My resultant. From where I started, that becomes my what? My resultant. You can see, guys, that this actually represent my what? So what I'm trying to show you is once you have drawn your vectors like this, you can come and measure this distance. You can come and measure this distance. You can come and measure this distance from here to there. You can come and measure that distance. So that distance now to say where you have started to where you ended here, that distance, when you measure it, it gives you what? 9.5 centimeters. When it gives you 9.5 centimeters, you now need to come and say, my resultant vector is equal to what? You now get to say, what is 9.5 centimeters in newtons? It becomes 9.5 centimeters times 10 newtons, because you know that 1 centimeter is representing 10 newtons. So this one becomes what? 95 newtons. So that is how you use graphical method to actually get to what? To calculate your resultant. So the first thing is to define your scale. After defining your scale, you determine the length of each vector using that scale, which is what you have done here. So we said 1 centimeter represents 10 newtons. So you divide 50 newtons by 10 to find 5 centimeters. You divide 45 by 10 to find 4.5. You represent this first vector by first choosing your reference point, and you choose the reference direction. We are going to the east. So your first would be starting from here, going towards the east. You can draw a sketch if you want to just have a sketch representation of what you want to draw, and then later draw up to scale. So the first vector has to be 5 centimeters. The second vector has to be 4.5 centimeters. So you draw exactly to say that 5 here. So there it has to be 5 centimeters, and here it has to be what? 4.5 centimeters. When you now get to draw a resultant line, which is starting from the tail of the first vector to the head of the second vector, you can be able to measure the distance in between. The distance, the total distance here, gives you your resultant. You convert that distance back to newtons. It gives you your resultant vector. So that is how you would have done it. So I would like you to take this question that I have given here as your practice that you need to do in terms of graphical representation, so that we can do algebraic calculations, and then we get to end our class. So let's try to do algebraic calculations. I'm sure you paused and then you took that question. Now, this one is saying a man applies a force of 5 newtons on a crate. So let's say we have got a crate and a man applies a force of 5 newtons, and then the crate pushes back on this man with a force of 2 newtons. Calculate algebraically the resultant force. So this is my crate, and then I need to choose my reference direction. I choose my reference direction for that first vector. So I will say that my first vector, which is F1, is going to the east. So I will represent that first vector to say that I'm pushing this crate with a force of what? With a force of 5 newtons towards the east. And then this crate is also pushing back with a force of what? Of 2 newtons. Now to determine the resultant here, my resultant has to be equal to what? This is F2. It has to be equal to F1 plus F2. Now I will need to choose a positive direction. So let me take east to be positive, so that my F1 would be positive. It will come and become positive 5 newtons. Plus my F2 would be a negative, so it would be negative 2 newtons. And then what becomes my resultant if I do that? 5 plus minus 2, it's more like 5 minus 2. So it's more like I'm saying 5 newtons minus 2 newtons. My resultant becomes what? 3 newtons. Since it's a positive, you can see that your resultant simply becomes 3 newtons towards the east, or else it will be 3 newton force of the man, of the force that is being applied by the man in the direction in which the man is applying that force. So it becomes 3 newton east if you said the man would be applying the force towards the east. So thank you so much, guys. That was the introduction of our chapter that we refer to, or else the broad topic that we refer to as mechanics. So I'm sure this has opened you to actually get to note that from now onwards, we can now get to start talking about different vectors, different physical quantities. We are now able to classify them into either vector or scalar quantities. After that, we are now able to actually get to represent vector quantities using arrows, and then we are now able to calculate different vector quantities. By doing that, we can now start on what we refer to as motion in one dimension. Because motion in one dimension, you need to understand the basics of what we refer to as what? The direction of a vector, and then after the direction of a vector, how you calculate that direction of the vector. And then thereafter, you can be able to calculate the magnitude. So now this was our class that we had. So by having that class, let's meet on our next class where we are now talking about motion in one dimension. After motion in one dimension, we then later go to mechanical energy. And then on our mechanical energy, we will now be done. So in summary, this is what we wanted to achieve. So we were introducing mechanics as a broad chapter. Now we have introduced that. We now want to go to motion in one dimension. So let's meet in our next videos to come.